Molar mass is part of the Flipped Learning in General Chemistry series. In this video, we'll review the concept of the mole and see how to use atomic masses of atoms to calculate formula masses of covalent and ionic compounds. We'll also start thinking about stoichiometry conversions in these types of problems. By the end of this video, you should be able to convert between grams and moles and understand the molar proportions of elements in a compound. Let's start by reviewing the concept of the mole. Avogadro's number, 6.022 times 10 to the 23rd, is a way to convert from the microscopic atomic scale to the macroscopic human scale. One atom is usually too small to be counted, but a mole of atoms makes a pile large enough to be handled by a person in a lab. The number itself is arbitrary. It's just a convention that chemists have agreed upon. Now think about the units for Avogadro's number. Mole is in the denominator, but what's in the numerator? It could be atoms per mole, or molecules per mole, or even moles per mole if that's what you're counting. The point is, the numerator is dimensionless, and that's what gives you the flexibility to count whatever objects you want. The periodic table gives us the information we need to convert between grams and moles. Atomic masses tell us the average mass of 1 mole of the element, and the unit for atomic mass is the AMU, which is equivalent to 1 gram per mole. This is a typical question you might see in class. How many moles are in 25.5 grams of water? Let's be explicit here and ask the question, moles of what? I'm asking for moles of water molecules. So to answer this, I need to know the molecular mass of water, which is the sum of the atomic masses of the individual atoms. I'll use this table to find the answer. Water is composed of two elements, hydrogen and oxygen, in a 2-to-1 ratio, and this stoichiometry needs to be accounted for. Each H atom weighs 1.008 AMU, but there are two of them, which means hydrogen contributes 2.016 grams to every mole of water. The atomic mass of the one oxygen atom is 16.00, so the total mass of water is 18.02 grams per mole. Now I can use this number to convert 25.5 grams of water into moles, and the answer, correctly rounded, is 1.42 moles of water. Water is a covalent molecule, so we called its mass the molecular mass. In this example, we'll determine the mass of the ionic compound sodium oxide. It's more properly called a formula mass because there's no discrete Na2O molecule. It's a repeating array of Na plus cations and O2 minus anions. We're going to calculate the number of moles in a certain mass of sodium oxide, and again I'll ask the question, moles of what? Even though there's no discrete sodium oxide molecule, we should do the calculation with the empirical formula Na2O. To determine the formula mass of Na2O, I'll use the same method as before. 2 sodium atoms plus 1 oxygen atom give a formula mass of 61.98 grams per mole. 53.1 grams of sodium oxide turns out to be 0.857 moles of Na2O. Okay, now I've changed the question slightly. How many moles of Na plus are produced when 53.1 grams of sodium oxide is dissolved in water? The answer to the moles of what question has clearly changed. Now I'm interested in the moles of sodium cations in the sample, but I can't just use the atomic mass of sodium because the 53.1 grams includes oxygen atoms as well. I have to start this calculation the same way as before, dividing 53.1 grams by the formula mass of Na2O. But now I need to add a conversion factor. The molar proportions in the formula Na2O tell me that 2 moles of sodium ions are present in 1 mole of sodium oxide, so I add this to my calculation. Being explicit with my units ensures I end up with the right answer, which is 1.71 moles of sodium ions. Okay, now it's time for you to try one on your own. Pause the video and answer these two questions. There are more atoms in the first problem, but the process is the same. Adding up the atomic masses of C, H, and O times the number of atoms in the formula gives a molecular mass of 180.15 grams per mole. Dividing this into the mass of aspirin gives the number of moles, 0.00180 moles. The second problem has one extra step because I'm asking for the mass of carbon atoms, not the number of moles. I start with the moles of aspirin from part 1 and multiply by the 9:1 ratio of carbon atoms per aspirin molecule. This gives me the moles of carbon, which I convert to grams by multiplying by the atomic mass of carbon. So there is 0.195 grams of carbon in the aspirin tablet, which is 60% of the total mass. Okay, that's it. Don't forget to complete the problem set and read the textbook sections assigned with this video. You should come to class prepared to convert between grams and moles. Thanks for watching.